In this video, I want to have a look at Simpson's rule. So in our last video, we had a look at the trapezoidal rule as a way of approximating an integral. Simpson's rule is another way to approximate an integral, but it does it in a different way. So the trapezoidal rule approximated our integral with a straight line. Simpson's rule approximates integrals with parabolas instead. So when we were using the trapezoidal rule, we needed two function values. We needed to know the value of the function at each of our bounds of our integral. For Simpson's rule, we need to know those two values, but we also need a third value. We need to know the value of the function at the midpoint of our bounds as well. Let's have a look at what Simpson's rule actually looks like. So we've jumped over to GeoGebra. We have this blue function here. Say we wanted to integrate this function between these two x values here. So we're trying to find the area underneath that curve. If we were using the trapezoidal rule, we would draw a straight line from this function value here to this one. So it would look like this. And we'd be finding the area of that trapezium. Now you can see in an example like this that that's going to way overestimate our area. It's not going to be very accurate at all. So what we did to try and make it more accurate is to use two applications of the trapezoidal rule instead. So we split our interval in half. We added a third point in there in the middle. And then we're going to apply the trapezoidal rule between those 2 points and between these 2 points. So we ended up with two straight lines and two trapeziums instead. And you can see that it's much more accurate, but it's still overestimating. Simpson's rule doesn't use straight lines. Like we said, it uses parabolas. So to draw a parabola, you need 3 points. So we've got 3 points here, our three function values, and we're going to draw a parabola through those 3 points. So it looks like this purple line here. So you can see that one application of Simpson's rule is much more accurate than our one application of the trapezoidal rule. But in the same way, we can get more accurate again by using two applications. So what we're going to do is we're going to add in a few more points. So we're going to use these 3 points here as our first application of Simpson's rule, and we're going to draw a parabola through those. Then for our second application, we're going to use these 3 points here. So this point right in the middle is actually going to be used twice, once in each application. So if we draw in our first parabola, or our second parabola, if we draw one in through those points, you can see that that's fairly accurately approximating that function. If we draw it in through our first 3 points, that's our orange line there. So between these two values, that's a fairly close approximation to that blue curve as well. So the more applications you do, the more accurate you're going to be. Now the Simpson's rule formula is given to you on your formula sheet that you'll have in every exam. So what it says is the integral between a and b of f of x dx is approximately equal to b minus a, so our upper bound minus our lower bound, over 6, outside of the function value at our lower bound, plus 4 times the function value at the midpoint between our upper and lower bounds, plus the function value at that upper bound. So let's have a look at an example. Our first example asks us to use one application of Simpson's rule to approximate the integral between 1 and 7 of 1 over x plus 1 dx. So before we start plugging everything in here, let's figure out what our function values are. So our function at a is our lower bound, so we want the function at 1. So we'd substitute 1 into here, so we'd have 1 over 1 plus 1, which would give us a half. Then we also want our function value at our upper bound, so function value at 7, which will give us 1 over 7 plus 1, so 1 over 8. And then we need the function value at the midpoint. So the midpoint is our upper and lower bounds added together and then divided by 2. So 7 plus 1 gives us 8 over 2, so we want the function value at 4. So substituting that in here would give us 1/5. So now we can apply the Simpson's rule formula. We're going to have the integral from 1 to 7, 1 over x plus 1 dx is approximately equal to 7 minus 1 over 6, outside of function value at our lower bound, so a half, plus 4 times the function value at the midpoint, plus the function value at our upper bound. And if we substitute that, put that all in our calculator to evaluate it, we'll end up with 1.41 recurring. So that's an approximation of that integral. Our second example asks us to evaluate that same integral, but it wants us to use 5 function values this time. So one application of Simpson's rule used 3 function values. 2 applications is going to use 5 function values. And the reason it's not 6 is that one of those function values is going to be used twice. So we're going to split this integral in half. So we've got the integral from 1 to 7, 1 over x plus 1 dx. We're going to split it. So we're going from 1 to 4 of 1 on x plus 1 dx, plus the integral from 4 to 7 of 1 on x plus 1 dx. And now we can apply Simpson's rule to each of those integrals separately and then add them together. So if we have a look at this first one, we need to know the function value at 1 and the function value at 4, so that's our upper and lower bounds, and the function value at the midpoint. So 4 plus 1 is 5, and 5 divided by 2 is 2.5. For our second one, we need to know the function value at 4, but we've already got that written here. We need to know the function value at 7, and we need to know the function value at that midpoint. So 4 plus 7 is 11, and half of 11 is 5.5. Right, so if we go through and figure all of those out, that's going to be a half, 1/5. This would give us 1 over 3.5, which is the same as 2 over 7. This would give us 1 over 8, and this would give us 1 over 6.5, which is the same thing as 2 over 13. So now we can substitute everything in. So we're going to have 4 minus 1 over 6 outside of a half, plus 4 times 2 over 7, plus 1/5, plus 7 minus 4 over 6, outside of the function value of 4, which was 1/5, plus 4 times the function value of the midpoint, which is 2 over 13, plus the endpoint, which is 1 over 8. Now if you put all of that, that should be an approximately there, sorry, not an equals. If you put all of that in your calculator, you'll get approximately 1.36, and that's to 2 decimal places. So this approximation here is much more accurate than our first approximation because we've used 2 applications instead. So that's an introduction to the Simpson's rule.